about principal component analysis. So we're moving a little bit to a different task than we've previously seen. We've been doing mostly density estimation prior to now. Now we're going to kind of get into what it's going to feel more like machine learning. So principal component analysis. Or PCA, as we abbreviate it, is a technique for several different tasks. Okay, so the first one of those tasks, I'm going to highlight in blue because it's going to be what we mostly focus on today. Okay, dimension reduction. It's also useful for data visualization. Feature extraction, topic modeling, and even noise reduction. Okay, so this is quite an old method. It goes back to Karl Pearson from 1901. So Karl Pearson was kind of an interesting guy. So probably you've heard of the Pearson's correlation coefficient. If you've taken statistics before, that's kind of one of the popular techniques for trying to measure significance. But Karl Pearson was kind of interesting as a person. So he's one of the founding fathers of a lot of the techniques that we use in statistics quite a bit, including PCA. He's a little bit of a complex guy, so he worked a lot with, he was a protege of this guy Francis Galton. And if you've heard of Francis Galton, you maybe heard about him in a statistics course where they maybe talked a little bit about regression, or if, actually it comes up a lot because he was a cousin of Charles Darwin. But both Pearson and Galton, I mean, brilliant men, came up with a lot of the important ideas in statistics. But they're complex because it turns out a lot of what they were doing ended up leading them to start studying eugenics and psychometrics, the measure of mental capacities, which of course these are both very complex and have a bad history and maybe topics. But also this goes back independently to another guy, Harold Hotelling from 1933, who actually named this principal component analysis. So we've referred to this technique the same way since at least 1933, although it goes by a whole bunch of other names. So it's so important that it's been kind of rediscovered or at least renamed and moved into a bunch of different areas. So it's called the Carhoeven-Loewe transform. That's from signal processing. Those are two, I think, Dutch guys. It's the proper orthogonal decomposition, in mechanical engineering. You've maybe seen it before in linear algebra, where some people refer to it as singular value decomposition or the Eckart-Young theorem. And in meteorological science, it's actually called the empirical orthogonal functions. But anyway, enough about the history of it. Let me give you an idea of what principal component analysis can do for you. So I'm going to give you two intuitive examples. And the first intuitive example is used in compression. Okay, so what I want you to imagine is that you have 1,100,000 by 100, we'll just say grayscale for now, pixel images of a rotated and translated smiley face. So it's the same, just white background, black, two eyes, and a smiley face, moved to different portions of the 100 by 100 square pixel frame, and then possibly translated also. Okay, so if you just take in that data set, right, you have 1 million sets of images, right, and the images themselves have 100 by 100 pixels, so 10,000 pixels. We'll say we can represent those with a single number. So in other words, we have 10,000 million numbers to store all of these images in their generic space. But you really know that you don't need all of that, right? So if I want to tell you which image I'm working with, I only need to tell you a few things, right? You already know, let's say you start out with the knowledge of what the initial picture looks like, the smiley face in the center of the white background. And I just can tell you, okay, shift it over, and up, and tilt it, twist it a certain amount. That's all you need to determine which picture you're actually looking at. So in other words, we don't actually have to store, so 10,000 million, by the way, is 10 billion numbers. We don't have to store 10 billion numbers. You need to store 10,000 values, right? The original image. You have to remember what that image looks like. And then for every one of those images, we just need to say, okay, move the top corner of the smiley face to this position and tilt it this way. So we have an X transformation, a Y transformation, and then a rotation. So really, rather than storing 10 billion numbers, we could equivalently exactly store the same information by just storing 3,010,000 numbers. Okay. And why does the 3 make sense to us? Well, there's 3 degrees of freedom in our transformation, right? An X rotation, an X translation, a Y translation, and then a rotation. Okay, so 1 million, 100 by 100 pixel images. Give myself a little bit more space. And we can go, instead of 10 billion numbers, we can compress without actually losing any information to 3,010,000 numbers stored. Okay. So this is a 3 order of magnitude compression. Because that's one intuitive example, right? You have these data sets consisting of images. The images live in a high-dimensional space, but usually, very often, they can be described by much fewer values. You don't have to save all of the values to get the same information from an image data set. So the second intuitive example you work for some arbitrary tech company. I guess let's give it a name. Maybe we'll call it Bookface. So let's say you have all of this data consisting of 2.4 billion Bookface user data. And let's say your task, you need to turn this data into some useful type of grouping. So, there's lots of these Bookface users. You want to group them into, let's say 5 or 6 kind of groups of types of users. But let's talk more about the data. Let's say that data, you work in Bookface, and there's many, many teams in Bookface doing lots of different things and collecting lots of different data. So let's say they're handing all of this data to you. You get these packages. You're like, okay, here's the big data set for Bookface user number 1, here's the big data set for Bookface user number 2, and so on and so forth. And you know that all that data came from lots of different teams, right? So probably those teams collected a lot of redundant data. If not redundant, definitely highly correlated data. So let me give you an example. Maybe one team collected the date of birth that users inputted when they first signed up for Bookface. And then another team collected the actual age that user is listing on Bookface, right? So those 2 things probably most of the time are nearly identical pieces of information. They're highly correlated, if nothing else. And so in whatever task you're going to do after with this data, whatever task that is, let's say it's this grouping task or clustering task, the amount of time it takes you to compute, to actually do your task, depends on the size of the data. So having all of that redundant data is bad for you, right? You don't want to have redundant data because it messes up, it kind of gummies up the works, and makes your methods take longer. So the main question that we're going to talk about today is how do we compress data and take advantage of data redundancy and correlation. Okay, so let me give you the idea of the PCA method. So the idea is we're going to use a projection, an orthogonal projection, on our data. We're going to project it onto a lower dimensional subspace. Lower dimensional subspace, while hopefully approximately preserving the geometric structures of the data. Okay, so what do I mean by geometric structures of data? So I'm going to, for now, just kind of zoom in on two kind of factors of data. So let me start with a little toy image. So let's say our data points are two-dimensional. The data points are going to represent blue. Okay, so let's say that is those little blue dots are our set of data. And there's sort of a couple of things that we generally like to preserve if we were going to push this down into a lower dimensional space. And those two things are we'd like to preserve how spread apart the data is and how close the data is, okay? So let's think about this, right? If we think about how spread apart this data is, it's much more spread, it looks like, in this direction, right? And it seems to be generally much closer together to one another in this direction. So that's exactly what we're going to try to exploit. We want to find some subspace. So a subspace, right? We're in two-dimensional space. We have a choice when we're in two-dimensional. If we want to go to a lower dimensional subspace, we can either go to a zero-dimensional space or a one-dimensional space. Let's go to a one-dimensional space, which is this line. And we want to find this line so that the projections, the orthogonal projections of the data onto this line are not too far, right? Right? Like something like that. We want those distances to be as small as possible collectively. Now there are two formulations of what I've just described, right? Trying to keep variation in the data and find a subspace that's collectively close to all of the data. So the formulations are these two. Are going to first, we could try to maximize the variance of the projections of the data, right? So let me kind of give a brief example. If we had instead turned this hyperplane, or excuse me, turned this line, right, and instead had chosen this line, a lot of these data points get kind of crunched into a small space. Whereas when we turn this line and we consider the projections, there's a much longer spread of the data, right? The variance of that data projected onto that one-dimensional subspace is much larger. And then the second formulation is to minimize the average projection distance. Okay, and the nice thing is that these two, we'll see, lead to the same algorithm. That algorithm is PCA. So either way you think about it, the line that you're going to get, the subspace that you get by trying to maximize the variance amongst the projections of the points onto the subspace, or by minimizing the average distance you have to project the points onto the subspace, those both lead to the same algorithm. So let me give you one more intuitive picture for why these two things are the same. So we're going to have the same set of data points. Our two data points are just going to be one on top of another, like this, these two data points. So these are the same, this is just multiple copies of the same image, right? Same data points. And I want to imagine what are some options for a one-dimensional subspace we might project onto. Okay, so some of the options, right? We really are able to choose any affine line, right? So we could choose this line, we could choose this line, we could choose a line that's way over here, which would be silly, right? But we can choose any line. So let's consider a few of them. Let's consider first this line, then let's consider this line, and then let's consider this line. Okay? And let's take a look at the projections of these points onto the line, right? So both of these points project onto the same point in this image, like this. Okay, so these are orthogonal projections. There's an orthogonal angle between the two of them, between the red line and the white lines. Orthogonally projecting onto this line, we get these two data points. Right? And then finally, orthogonally projecting onto this red line, we get data points that are the same, right? We don't change the data points at all. So it's unsurprising, right? This is obviously the best line. These points already lived in a one-dimensional subspace. We should pick the one-dimensional subspace they live in. If we chose something like this, right, this neither minimizes the variance. These points collapse to the same point, so we don't keep any distinction between them. And the distance they had to move to get onto the line was large, right? If we started tilting the line, we see that we're increasing the variance. The points are spreading, these green points are spreading away from each other as this line tilts. And these white lines are getting shorter until we get to this ideal hyperplane, which is where the distance, the variance between the two green points is largest, and the distance to the red line from the blue points is the shortest. Okay, so let me set up our general scenario. Okay, we're going to imagine we have a bunch of data observations. Okay, so these are our blue points, and I'm going to represent them by vectors xi, and I'm going to say there are n of them, and they're all capital D dimensional vectors. And then our goal is to project the data onto a lower dimensional subspace. I'm going to say that this is going to be an m-dimensional subspace. Okay, and like I said, lower, right? So I want m to be smaller than the ambient dimension of the space, which is d. Okay, m should be less than d. Okay, and this subspace, once we produce it, is going to be called the principal subspace. So that's what we're looking for. So in order to describe the principal subspace, we just need a basis for the subspace. So we need a basis for the subspace. Okay, and that's going to consist of m vectors, right, because it's an m-dimensional subspace. And they are going to live in our ambient space, so they are d-dimensional. Okay, so we need m d-dimensional vectors, and I'm going to name these, I'm going to call them vi. Okay, so it's going to be a basis, vi from I equals 1 to m. That's the basis for the principal subspace. And then, right, if we actually want to project all of our data points into the subspace, we need, for every one of the data points we have, how to describe them in the subspace spanned by the VIs. So we just need coefficients, right? So we need coordinates. All endpoints in the subspace. So this is n sets of m numbers, right? Or n m vectors, if you want to think of it that way. Okay, now let me give us a few assumptions we're just going to make for simplicity. So the first assumption, okay, is on the dimension of the subspace. So rather than just considering the general case first, we're going to start with the case that the subspace is one-dimensional, right, which means it's a line, an affine line in space. And we can generalize this via induction later. And then the second assumption is that the data is centered. And what that means, the data being centered, means that if you think of roughly the center of the data, it should be the origin. Okay, so that means that when you take the average of all of the data points, okay, which I'm denoting x bar, that's the sample mean, we should get the origin. If your data didn't start out centered, is it hard to center it? No, right? All you have to do is subtract off the sample mean for every point. So you should check that if you add up xn minus x bar, that you do get something that's centered. Or sorry, that you do get the origin, excuse me. Okay? And then the third thing is that the basis that we're going to find this set of VI vectors is orthonormal. Okay, now this isn't really an assumption, it's just a choice. So to describe a subspace, we definitely need a basis. If you have a basis, though, you know that first you can orthogonalize it, and second, you can normalize those orthogonal vectors. So this is not really a restricting assumption at all. It's just we're telling ourselves we're going to seek vectors that have orthonormal properties. Okay. So let me start, we're going to think about the minimum error formulation, right? So I said there were two formulations, they led to the same algorithm. Let me present the idea. So the minimum error formulation, the idea is just what it sounds like. We're going to minimize the sum of the distances between points and their projections. And there's two main steps to this. The first one, we're going to write the errors, so the distances between points and their projections. And these are their projections onto the principal subspace. Okay, and then the second thing we're going to do is we're going to choose the basis vector, right? We're thinking m equals 1, that minimize the mean error, or the average one of these distances we just wrote down. Okay, so let's do this. So the first one, part 1, we need to write down the errors between the points and their projections. So let's think about what we can say about the points and their projections. So first of all, our principal subspace, right, because we're one-dimensional, is a line through the origin in the direction of the basis vector v1. Okay? So the projection of xn, the nth data point, onto the subspace, right, the subspace spanned by v1, is just given by this point, right? We take the inner product between the direction v1 and the point xn. That's giving us the amount that points in the direction v1 of xn. And then we point that in the direction v1. Okay? Okay, so the picture might be helpful here. So we got our data point, and say this is xn. Okay. And got this line. This line is the subspace which is spanned by the vector v1. And then if we project onto this subspace, that gives us this projected point, which is v1 transpose xn, the inner product between v1 and xn, times the vector v1. And if we look at this distance, this is that distance exactly, v1 transpose Now, one thing I want you to note is if we take any of our points and project them onto this subspace, we're always going to get something that looks like this, right? It's some value times the vector, the direction v1. So equivalently, we don't need to keep track of this v1. We can think of these as scalar values. They're entirely, all the points are determined exactly by their distance along that line. Okay? So we can start thinking of this instead as this is now the point once it's projected. Okay. A quick note that will be important for us is that the mean of the projections is 0, is the origin. Okay. And to see this, let's just check, right, when we take the average of all of the projected data points, so that's v1 transpose xn times v1. When we take the average of these values, with a little bit of simplification, we can see this right away, right? So first, pull this v1 outside. So let's slap some brackets around this. And now we have the average of the inner product v1 transpose xn. Again, v1 transpose, this is linear, so we can pass this average, this summation, and the multiplication by a scalar in on top of this xn, and we end up with v1 transpose the sample mean of our data points times v1. Now, the sample mean of our data points, we assumed right over there, the assumption was that this was a centered data set. So this, the average is 0. So we have v1 transpose the origin, which is always 0, times v1, which is origin, right? So the mean of all of the projections onto this data set, just like the mean of the data points initially was the origin, the mean of their projected data points is on the origin. And what this tells us is that the mean of the data, the origin, original data, lies on the principal subspace. This will be the case even when the data is not centered. We might have time to see the generalization. Okay, so we're still wanting to work with the error between the points and their projections. We now have a good description of the projections of the points. So what is the error between points and their projections? Okay, so let's just write it down. The error is the distance between the nth data point and its projection onto the subspace, which was v1 transpose xn times v1. Okay, and let's just look at the squared distance, the squared error. So this is the same thing as taking the inner product of this vector with itself. So this is this is equal to the squared norm of this vector. So now we can kind of do these out piecewise. So the inner product of this xn with itself, xn, is the norm of xn squared. We're going to have minus 2 this vector, v1 transpose xn times v1, inner product transpose with xn. Okay, and then we're finally going to have plus this scalar v1 transpose xn squared times v1 transpose v1. If we simplify this, v1 transpose v1 is 1, right? Because we assumed that our basis was going to be orthonormal. So we have V1 transpose xn quantity squared. And then here we've got a minus 2 V1 transpose xn quantity squared. So this simplifies to V1, this simplifies to the norm of xn squared minus the inner product of V1 with xn quantity squared. So now let's write down the mean error. So the mean error is then the average of all of these terms, right? Right, which then ends up just being the average of these simplified terms. Okay, so we have the average of the norms of the xn squared minus this inner product squared. And then we're taking the average of that. Okay, now we want to minimize this. And what are we really minimizing with respect to? What are we choosing? Well, we're choosing the subspace, right? And the subspace is entirely determined by the vector v1. So we want to choose v1 that is going to minimize this average error, right? We can't do anything with the data points. Those are fixed, right? We don't get to control those. So to minimize this, we really just need to maximize the squared inner product sitting right here, okay? So choose V1 to maximize this average squared error. Right? Maximize this average squared error. And let me just do a quick little simplification. So notice what we have in here, I mean, it's fine, but I'm going to introduce something to make it look a little different. This is V1 transpose xn minus, I'm going to introduce V1 transpose sample mean x bar, right? I haven't changed anything. Why? Because this inner product, V1 transpose sample mean x bar, we saw was 0, right? That was from the fact that our data was centered. So this is just minus a 0 term. But I want to write it this way because it's more useful for us later. And what's sitting right here, this term, is the sample variance of our projections. Okay, so why is this the sample variance? Well, remember, variance is always the random variable minus its mean in quantity squared and then the expectation of that. So this average is an expectation of the inner product minus the average inner product, quantity squared. Okay, so that's the sample variance. So what we see thus, we see that minimizing the error is we worked with the error. We found out the only part of it that depended upon V1, upon the subspace vectors, was this term that with a little bit of rewriting is just the sample variance of the projections. So minimizing error is exactly equivalent to maximizing the sample variance. Now to maximize, note first that we can do a little bit more simplifying that will make this look a little nicer. So we have 1 over n, the summation of V1 transpose xn minus V1 transpose x bar quantity squared. Now I'm going to do two things at once. I'm going to separate these. These are a squared term as this times itself. And I'm going to pull out the V1. Okay, so this is equal to the average of V1 transpose xn minus x bar, right? I just pulled the V1 out. And I'm going to multiply at the same time, right, with this itself again. But now I'm going to use the fact that when you take the inner product of two vectors, right, that's symmetric. So x transpose y is y transpose x. So this is xn minus x bar transpose V1. Okay? And then finally, I'm just going to apply literally associativity of matrices, right? So this is the product of two matrices, and this is the product of two matrices. They form each scalars, so 1 by 1 matrices, and then we multiply those in the middle. I could have equivalently have multiplied this matrix times this matrix first, and then the matrices on the outside. So if I do that, and I pull this averaging inside, I get V1 transpose this average times V1. Okay. And I'm going to rename this as S. Okay, and S here is the sample covariance matrix. Right? So it looks a lot like a covariance matrix, and when we consider just the average, the mean, and the sample, this is the sample covariance matrix. Okay, so we want to maximize this, which means we really want to maximize this, the inner product, or sorry, the quadratic form defined by V1 transpose S V1. Now the first thing to note is that this objective is unbounded if we let the norm of V1 go to infinity, right? Because if we got a positive value and then you just multiply V1 by 1,000,000, it's now 1,000,000 times, well, actually 1,000,000 squared times that positive value, right? So we need a constraint. And we're going to make use of the constraint. That we've used before, which is that our vectors, right, our V1s are from an orthonormal basis. So they have norm 1. Okay. Right, which this is equivalent to instead writing that V1 transpose V1, which is the norm squared of V1, is equal to 1. Okay, so we're going to use this form. Right, and now we want to maximize a continuous objective function subject to a constraint. So in order to do that, we're going to introduce a Lagrange multiplier. Okay, so just to remind you, a Lagrange multiplier is pretty simple. So it says, we're going to use it in this way. If we have our objective function, which is a function of our choice of V1, this is V1 transpose S And we have our constraint function, which is g of v1 is equal to v1 transpose v1 minus 1, right? We want that g to be 0, and we want to maximize with respect to f. Then we know that at the optimum, so at the optimum with respect to f, subject to the constraints given by g equals 0, we have the gradient of f is equal to lambda 1, I'm just naming it lambda 1, times the gradient of g. And when we work with our specific objective function, so here we're going to take the gradient of this with respect to v1, we get 2 times s times v1, and that should be equal to lambda 1 times the gradient of this function, right, which is just 2v1. Okay, which leads us to s times v1 is equal to lambda 1 times v1, right? And what is that equation I have written there? Well, right, that means that when you apply the linear transformation corresponding to s to the vector v1, it just scales that vector. What are those types of vectors called? They're called eigenvectors, right? So we know that v1 is an eigenvector of the matrix S. And to see which one is it, we need to look back at the objective function. So notice that the objective function, which was v1 transpose s v1, if v1 is this eigenvector that we've described there, then this is equal to v1 transpose lambda 1 times v1, right? So we apply s to v1 and it just scales it, which is equal to lambda 1 v1 transpose v1, and again we use the constraint that this is equal to 1. So we end up with just lambda 1. So if we want to maximize this objective function, which is equal to lambda 1, by choosing the appropriate eigenvector, we should choose the eigenvector associated to the biggest eigenvalue. Okay? So we choose v1 equal to eigenvector associated with largest eigenvalue. Okay. And so this is in general what we're going to do. If you want, let's say, an m greater than one dimensional subspace, you're going to construct it by forming its basis vectors as the m eigenvectors of S associated to the m largest eigenvalues of S. Okay? And there's quite a bit more that we can see from this, but I don't have time for that. And instead, I would recommend that you take a look at the code for today, which is going to be very useful for you. It'll give you an idea of how applications of PCA actually work. And we're going to apply PCA to a data set consisting of a bunch of images